Now, let's start. Nevertheless, there is a whole number, well, it's actually an entire zoo of topological properties that are heavily used. There is separation properties, which I'm going to write down now. Then there is connectedness, path connectedness, simple connectedness, Hausdorff is a separation property. There is compactness, paracompactness. There is a very long list, and there's actually a book that's, I don't know what the title is, it's kind of topological properties, and for many, many spaces, hundreds of properties are listed, and whether this space has the property or not, but no such set is sufficient. You always find sets, two sets that are not homeomorphic, but share all those properties. So, okay. Anyway, so, but these, apart from serving in a future classification, possibly, these topological properties are important in themselves. And so we start with topological properties. Topological properties 1, separation axioms or separation properties. Definition. A topological space MO is called T1. That's the property. It's called T1. It's called T1 if for any two distinct points, that means P point P, that's not the same as the point Q, there exists an open neighborhood of P, there exists a U in the topology that contains P, there exists an open neighborhood of P such that P does not lie in U. Or one can write this differently, that the set with the element P does not intersect U, meaning that the intersection of this one point and the U is empty. Such a space is called T1. Definition. A topological space MO is called T2, and that has another nicer name that's called Hausdorff. Hausdorff actually came up with the topological axioms. He formulated them in terms of neighborhoods, but they're fully equivalent to the set I wrote down, to the set of axioms I wrote down in the beginning, defining it by open sets. But Hausdorff had one additional axiom compared to the three, and that one is called the Hausdorff axiom. Nowadays, because so many interesting topological spaces do not have that property, one removed that axiom from the general definition of topology. But because for many spaces, I mean, Hausdorff was very clever, he came up with the whole thing in this abstraction. Very often you you want this additional property. You call it T2 or Hausdorff. If for any two distinct points, for any P not Q points, like here, there exists an open neighborhood of P and an open neighborhood of Q such that the intersection of the two neighborhoods is empty. So if one wants to draw a picture intuitively, well, intuitively, we better say what topology we take. We take R2 and equip it with the standard topology. I have this point and this point. If they're distinct, I always find an open set around here and an open set around here, such that the open sets do not intersect. It's a separation axiom. Now, this here, the T1 property is for any two distinct points, P and Q, you always find an open set around P such that the Q doesn't lie in there. You see, this is stronger. Here you need two clouds around each point, two open neighborhoods. Here you need only one such that this doesn't lie in there. And there are examples for sets that are T1 but not T2 and so on. So example, RD with the standard topology on RD is T2. And hence it's T1, right? T1 is weaker than T2. But then there are other examples, like for instance the Zariski topology. That's a topology that appears in algebraic geometry. That is T1 but not Hausdorff, but it's not T2. And there will be a problem on the problem sheet for the Zariski topology, and the Zariski topology is very important in algebraic geometry and push the subject forward. So that's a very important topology. And there are further separation axioms, so remark. There's also T3, more impressively, T2.5. I like this. So T2.5 is, you have two distinct points, and around one of them, there's actually a closed neighborhood, such that it doesn't intersect with the other point. Okay, so that's T2.5, and then there's T3 and T4 and whatnot. Okay, there are stronger and stronger separation axioms, and yeah, the original one by Hausdorff is that one, but you see there are situations in which you want one and then the other and so on. So, okay. So T3, what is T3? T3 is you have not 2 points, but you have a closed set and a point, and around the closed set you find an open set such that that doesn't intersect with the point. So you come up with crazy stuff. They all have their application in some branch of mathematics. Also on the problem sheet will be the proof that in a Hausdorff space, so in a topological space that is Hausdorff, you can prove that every sequence that converges has a unique limit point. And that's a very intuitive notion. It converges to a point, well, then it doesn't converge to another point. Well, for the chaotic topology, that's not the case. As we saw, every sequence converges against any point. Well, if that is true, what I just said, that in a Hausdorff space, if it converges, the convergence point is unique, that already shows that the chaotic topology cannot be a Hausdorff space. Of course it's not. So counterexample to T2. Counterexample to T2 is M equipped with the discrete, with the chaotic topology, because you choose any 2 points in P, in M, and now you need to find, well, it's not even T1. It's not even T1, because you will never find an open set in which P lies that doesn't contain Q, because the only open set in which it can lie is all of M. That's on the problem sheet. So we continue our list of topological properties, and as I mentioned, there is no complete list of topological properties that you could require for a topological space, such that if you had 2 topological spaces which differed in at least one of this complete list of topological properties, you could already conclude they're not homeomorphic. Indeed, no such list is known. Nevertheless, in many circumstances, it's very convenient to add to the axioms of a general topological space additional special topological properties, sometimes in order to be able to prove some theorems that you couldn't prove without having that property, sometimes in order to understand the situation better. It very much depends. Now, the next pair of properties I would like to talk about are compactness and paracompactness. So these are 2 very heavily used topological properties, because indeed, very often, if you want to prove some theorem, in some setting to which a topological space is an underlying structure, very often you would first tackle the proof in a compact case, because usually proofs are simpler there, and once you understood the problem in a compact case, you'd try to extend the theorem to the non-compact case, which sometimes simply is not possible, but sometimes it is. Paracompactness is a much weaker notion than compactness. In fact, it's so weak that it's very difficult, or very difficult to find any topological spaces that appear naturally, if you wish, that are not paracompact. I'll present a theorem to that effect. And for manifold theory, which will be our concern later, paracompactness is a fundamental assumption that we will always make, similar to the Hausdorff assumption, because Hausdorff, so that was the T2 separation property, Hausdorff plus paracompactness gives us a very convenient property of a space, namely that there exists a so-called partition of unity. That is what I'm going to present now. But let's first start with the definition of compactness. A topological space MO is called compact if every open cover has a finite subcover. What does that mean? What is an open cover to a topological space? That's a notion that's useful to know on its own. An open cover, so if C is a subset of the topology of the space, so it's a collection of open sets, then C subset of O is called an open cover if, very simply, the union of all the sets in C already recovers the entire topological space. It's the very intuitive notion of covering the topological space. That's an open cover. What is a finite subcover? So let's be more specific. If every open cover C has a finite subcover C twiddle. A finite subcover is a cover C twiddle. So a subcover is not less than a cover. It's certainly as well a cover. It's a cover C twiddle, such that for every element in the cover, for every open set in the cover we have, there exists an element U twiddle in C twiddle such that U hang on a second. For every U in C, there exists a U twiddle in C twiddle. No, this is already the refinement. Hang on a second. That's too weak. Aha, yes, it's a subset of the cover. So I already wanted to write down something weaker, which is coming in a second, is a cover such that C twiddle lies in C. And it could be C already. So you take a cover, it's a cover, and a finite subcover is you take out open sets from the cover, but you still have a cover. And if that cover is finite, then you have a finite subcover. So a finite subcover is a cover which is a finite subset of the cover. That's it. That's a compact space. And very often one wishes to look at a subset. Definition, a subset N in M of a topological space M, so we still have the topology on M, is called compact. Well, obviously, we have to get a topology for N if it is compact, or if N equipped with the topology of M, that's topology on M, but induced on N, is compact as a topological space. So by equipping the subset with the subset topology, you make it into a topological space in its own right, and if that is compact, then the subset is called compact. Very simple. Now, this cover and subcover business makes it manifest that compactness is a topological property. Any property that's defined only in terms of the topology is a topological property. In particular, if you have two homeomorphic topological spaces, they will share these topological properties. So if MO is a topological space and NO prime is also a topological space, and they're homeomorphic, so there exists a homeomorphism between them, an invertible map which in both directions is continuous, then if one of the spaces is compact, the other space is compact too. Very often you check compactness or any topological property by finding an appropriate homeomorphism to a space of which you know the property. Anyway, so but this makes this very explicit that it's a topological property. It sometimes makes it hard to prove. And there is indeed a very important and famous theorem, and that's the theorem of Heine-Borel. And that says, in a metric space M, D, and if we say in a metric space and we talk about topology, we always assume that is equipped with the metric-induced topology. Every closed and bounded subset of M is compact. Okay, in a metric space. So I should explain this a little. What precisely do we mean by a metric space? There are different notions of metric in mathematics, and the metric we mean here by a metric in this context, one means a map D that takes two elements of the space and maps it to a non-negative real number such that the following properties are satisfied. First, the metric acting on Mn is the same as the metric on Nm. That means from Paris to London, it's the same distance, like as it is from London to Paris. B, you have a positivity property that is dMn is always greater or equal to 0, and equal if and only if m equals n. So two distinct points have always a non-zero distance. And property C is the triangle inequality. If you go from A to B and then you go from B to C, that ought to be always a bigger distance or the same distance as if you went from A to C directly. It's a triangle inequality. So it's this notion of metric. Later on in this course, we'll meet a notion of metric in differential geometry, which is quite a different beast. From such a metric in differential geometry, under certain circumstances, you can extract such a metric on a manifold, but not the other way around. So that's a metric space. So what's the metric-induced topology Well, you probably guess the metric-induced topology is defined very much like we defined the topology of RD. So I write similarly defined as standard topology on RD, but the only thing that differs is that the balls are now somewhat defined in a somewhat more general way. The ball around a point P, a ball with radius R in R plus, around a point P of the topological space is the set of all Q such that the distance from Q to P is less than R. So you see, instead of some norm, which clearly induces on RD, where you have an addition, a subtraction, and so on, for addition, where a norm can induce such a metric, but there are spaces on which you have no addition. You couldn't take the difference between 2 points to then find the norm. Then you need a more resolved object that is able to eat two such metrics. Very famous is the French railroad metric. The French railroad metric works like this. You have Paris, and you have, say, Marseille and Calais and Nancy, something like this, okay? And the intuition is, if by train you want to go from Marseille to Calais, the only way you can go is via Paris, because everything goes via Paris. Every train goes via Paris. And so you can assign distances here, but if you want to go from Marseille to Nancy, you first go to Paris, then you go there, and the distance is the sum of those. So this map that assigns then the distance to all these pairs of points in such a geometry, that satisfies the conditions of a metric. But it doesn't satisfy the conditions of a norm if you thought of the world being a plane, at least as far as France is covered. You see the differences and then the norms. You wouldn't find a norm that reproduces the French railroad metric. Okay, so the metric is something more general than what can be constructed from a norm, but for any such you can define these open balls and you can induce a topology. Okay, so what a closed subset with respect to some topology is, we know. The question is, what is a bounded subset? Now that is now not very difficult. You just find a number such that all the points of this subset lie within, say, a circle of a certain radius that is constituted by that number. If that's a finite number, then the set is bounded. Okay, very intuitive. Okay, so after all these definitions have been made, the important thing is Heine-Borel says in a metric space, or a space that can be equipped with a metric, and then you find the induced topology, every closed and bounded subset is compact, with respect to that induced topology, of course. Yes?
Why is the metric-induced topology an element of R plus and not of R plus 0, like the metric space form?
You mean this one?
Yeah. Well, the metric-induced topology on bottom.
Yeah.
Why is that only element of R plus?
No, sorry. So this R, this radius, is supposed to be greater than 0. Yeah. So my
okay.
My notation gets more and more cryptic, but I mean this R is just supposed to be a non-negative real number. Okay, so that's Heine-Borel, and obviously in many circumstances you would have a metric space, so it's very easy to decide for a closed and bounded subset that it's compact. Okay, so let's have some more examples. So A, the interval 0, 1 is compact. Okay, as a subset of the real line, which is a metric space, because on the real line you can establish a metric by taking the difference between 2 points and then taking the absolute value. That will give you a metric. It's compact in that sense, according to Heine-Borel, but it's also compact as a subset of the real number, with the topology on the interval being the induced one from the topology on the whole real line. Well, of course, it must be, because Heine-Borel holds. Okay? So that interval is compact. The real line is not compact. Not compact is usually easy to see, because you just have to find one cover that does not have a finite subcover. Proof: construct a cover that has no finite subcover. Okay? That's the real line. And I take there's no colored chalk, okay? That's bad. And I take this cover, that's not a cover yet, so now I cover the real line by these guys. If I take them all together, it's a collection of open sets, and they cover the entire line, because their union recovers the entire line. Okay? But it has no finite subcover. They're obviously the set C, so this is the set C. This is has obviously infinitely many elements. Now, if you want to find a subcover that's finite, you have to take some of the elements away, obviously. But if you already take only one of them away, the cover property is violated. If you take one away, you have a subset. Well, you can take many, well, but there is not even an infinite subset that is still a cover. Much less is there a finite subset that's still a cover. Hence, not compact. Okay. Improvement. Okay, so as I said, this notion of compactness, that's important. So, quick theorem. Once you have your collection of compact spaces, you can construct new compact spaces by looking at MO, MOM, and NON, topological spaces that are compact. Then it follows that the Cartesian product of the two spaces, how do I make them into a topological space? Well, I can equip them with the product topology. Then the Cartesian product of the topological spaces is again compact. And if this works for two Cartesian factors, it works for finitely many. So compactness is inherited to finite products. That's good. Now, however, compactness is a very strong property, and sometimes it simply doesn't hold, but still there is a much weaker notion, and that's paracompactness. A topological space MO is called paracompact if every open cover of this topological space has a local refinement, So let's say, again say if every open cover C has a local refinement C twiddle, has an open refinement, has an open refinement C twiddle that is locally finite. What does that mean? Well, an open refinement C twiddle of a cover is again a cover C twiddle, but now such that for every U in the original cover, there exists a U twiddle in the refinement such that U twiddle lies in U. That's an open refinement. Well, it's again an open cover. So it's a cover consisting of open sets. We're only considering open covers here. If I should write cover without open, I always mean an open cover. Now, when I wrote down the definition of compactness and I wrote down the definition of subcover, I started out like this and I said, no, that's wrong. This is wrong. The point is that any subcover is a refinement but not the other way around. Okay? Now, locally finite, what does locally finite mean? Locally finite means that for every point P in our topological space, there exists an open set U that is a neighborhood of P. So there exists a U in O that contains P such that, so we're talking about the open refinement that's locally finite, such that the intersection of U with elements with a U twiddle from C twiddle is non-empty only for finitely many U twiddle in C twiddle. So I should delete it here. Okay? So that if you go to a point in the manifold, you find a neighborhood such that this neighborhood has a non-vanishing intersection only with finitely many open sets from this refinement. Well, that definition is quite a bit, but it needs to be made in this way in order to be useful. Now, essentially from here, you have the immediate corollary that compact implies paracompact. So my assertion that paracompactness is a weaker notion than compactness is shown this way. Compact implies paracompact. Okay. Now, let me see whether I first... Okay. So there is a theorem by Stone that says every metrizable space is paracompact. This is due to stone. A metrizable obviously means that you can equip it with a metric that then induces the topology. Every metrizable space is paracompact, and that already shows you how generic this notion of paracompactness is. Yeah, there are spaces that are not metrizable. There are spaces on which you cannot put a metric. I'll give an example in a second, but it's a very exotic and artificial example. But for most spaces in physics, well, maybe not all, but for most, it's actually paracompactness. It's not a very strong condition in that sense, but it has a very important implication, which we're going to talk about in a second. So let me give you two examples. So RD equipped with the standard topology on RD. Sometimes I will probably forget to mention with what topology I will equip RD, but whenever I don't specify, I mean the standard topology. That's the standard convention. It's just, especially in the beginning, it's useful to always remind oneself RD can be just a set, the tuples, the D tuples. It could be a set equipped with an addition, it's then an additive group. It could also have an S multiplication that makes it then into a vector space. Okay. Then on top of it, it could have a norm, then it would be a normed vector space. From this norm, you could then make a topology and make it then, at that level, a topological space, which then is this one, and so on. So you always think of the different levels of structures you have, and always remind yourself, if you do certain constructions, how many of these structures do you really use, right? In physics, very often we say, well, RD is equipped with just everything. You can add, you can subtract, you have everything at the same time. But very often we will not meet RDs that have so much structure, but nevertheless you still have this, you know. That's just a reminder. Anyway, RD with the standard topology is paracompact. And well, if you have Stone's theorem, of course, because you equip it with a norm, and the norm will produce this standard topology. The norm makes it metrizable, or induces a metric in the obvious way, like I explained before. So it's paracompact. That's good. And B, there's a thing called the Alexandrov line, or the Alexandrov long line. That's cute. And so the idea here, I'm not going to write this down. So I first say it's not paracompact. It's a counterexample. It gives you a taste of how artificial such spaces are in some sense. So the idea, I just sketched the idea. The idea is that the standard real line can be understood as taking the interval from 0 to 1, left close, right open, and take this and then put another one, attach another one to it, and another one to it, and another one to it. So it's a little bit like take many of those. Okay, I already write Z across this, which is intuitively looks like this. This, and then this one eats again that one. This one eats again that one. This one eats again, and so on. Okay, so you take a ruler and always put one ruler next to the other, and you recover the whole real line. So the real line is kind of like a countable product of this interval. That's the real line, and that's paracompact. That we already saw. So the idea of the long line, let's call it L, the long line is now taking this interval, but not taking it countably often to get the reals, but taking it uncountably often. So this is a non-countable set, or non-countably often, non-countable set. And this is from the theory of ordinal numbers. That's the the smallest such ordinal number that's not finite. Well, don't ask. If you want to read up on this, read up on this. The idea is take this non-countably often, and then you get a non-paracompact topological space. And of course, you induce the topology and so on and so on. This is rather artificial, and the other examples that at least I know of are also rather artificial. So that's the intuition. Paracompactness is actually something rather natural. Questions so far? Yeah?
What is the definition of metrizable?
Aha, a metric can be found. So every metrizable topological space MO is paracompact. A metric can be found such that the topology is induced by the metric. And or in other words, every topological space where the topology is the one or equivalent to the one induced by a metric is paracompact. Okay? And you know that we had this before, that a topology, if you define it by virtue of these open balls and so on, the open balls can have different shapes and forms, and that can produce quite the same topology as another shape or form of the balls. Okay? So metrizable, it doesn't want to specify which metric it is one that reproduces this. It can only be understood in this way because paracompactness relies on the topology, so you need to make a connection between this metrizability and this topology and so on. Okay, good. Yeah?
One question towards the Alexandrov long line.
Yes.
How can I really imagine that? Because you just said, like, for a paracompact line, so you can imagine stacking ruler on ruler, infinite amount of rulers along the line. But how can I imagine like this Alexandrov long line? Well, is it like a set of infinite amount of points, or how can I?
Well, it's a non-countable set of times you put this after the. Well, I don't know. Intuition escapes me there a little. I mean, you could already argue this is already difficult to imagine. Now you have to go in both directions to infinity. Well, yeah, maybe you can think like this idea of potential infinity and so on. These are all old ideas. The difference here is countable product and non-countable product, and that destroys the paracompactness. Okay. Okay, so I mean, there are proofs for this, and obviously you have to use this omega-1 set, this first non-finite ordinal number, and so on, and in order to prove this. Okay, one remark. As you see, for many of the theorems, and I do not present proofs here because they're rather involved. Okay, and this being a physics course after all. It's important to understand the notions, understand the definitions very precisely, know where they are applied, and get a feeling for how these notions are connected, okay? And also how to construct new spaces with such properties from old spaces, because at the end of the day, you'll have a certain toolbox of spaces of which you know they're connected, they're compact, they're Hausdorff, and so on, and you compose them, and you understand many situations this way. So kind of from a higher point of view. You can always go to a topology textbook and look up all these proofs. We just don't have the time, otherwise we spend the entire semester on topology. But nevertheless, it's very valuable to look at these different examples and look at the different theorems that I present in order to get an overview over this subject, which in many cases is fully sufficient to come to physical applications and to understand them full well. So let me give you one more theorem. Let MO be a paracompact topological space, and let NON, OM, be a compact, not paracompact, only compact, not only, even compact topological space. Then M Cartesian product N is again paracompact. And if I write something like this, strictly speaking, this is only a set. It's just a Cartesian product. A set cannot be paracompact or not. A set is a set, it's not a topological space. But again, if nothing specifically is said specifically, then we equip always the Cartesian product of two sets which each carry a topology with the product topology, is the understanding. So you see, paracompactness doesn't behave quite that well under product taking, Cartesian product taking. One of the spaces needs to be compact. Corollary, if you have a paracompact space M, then you can only attach a finite number of compact spaces in order to have a paracompact space again. Well, at least to be guaranteed to have a paracompact space again. Okay, so again, like before, compactness abstractly defined in terms of covers and the existence of finite subcovers, but then intuitively very well understood for metric spaces in terms of the Heine-Borel theorem. For paracompactness, there is even a sufficient and necessary criterion to understand it, and that is sometimes taken as, and I'm going to present this in a second, and this necessary and sufficient criterion is sometimes taken to be even the definition of paracompactness and will play an important role in manifold theory. So this criterion I'm talking about is the following theorem. And it's not valid for every paracompact space, only for Hausdorff paracompact spaces. So let MO be a Hausdorff topological space, MO, then it is paracompact if and only if and only if every open cover of that space, of course, admits a so-called partition of unity subordinate to that cover. Partition of unity subordinate to that cover. Well, obviously that requires some explanation. Okay, what is a partition of unity? So if and only if every open cover, which we give the name C, admits a partition of unity subordinate to that cover. So a partition of unity is the following. Subordinate to the cover is the following. It's a set curly F of continuous functions, continuous maps, if you wish, continuous functions. Well, let's say one such f, small f, goes from functions on this set, but they only map into 0, 1. So if I say continuous functions from M to 0, 1, obviously I can only speak of continuity if I know the topology on M. Well, I do. It's O. And I know the topology on O, on the interval O1. Well, that's, of course, the induced subset topology from the real line, because I said nothing different. It's a set F of continuous functions F such that A for every F in that collection, there exists a U in the cover. So you see it's the partition of unity subordinate to a given cover. So you find these functions such that there exists a U in C such that f of p, this particular f of p non-zero, implies that the p already was in that element of the cover. You could also say the function f has only support, has support only on that set U. That's the first condition. The second condition is that for all points in the manifold, there exists an open neighborhood long word for saying exists an open neighborhood V that contains P and that itself is open. There exists an open neighborhood such that V intersection U non-empty only for finitely many U in the cover. And if that's the case, and then we can look at the function f, or all the function f's, f for these finitely many U on the cover. So only for finitely many U1 to UN in the cover. And then you can look at the corresponding Fn, and there are only finitely many n, and you require that on V they always sum up to 1. And that's the partition of unity. And the whole business with the finiteness is there in order to have a finite sum instead. I'm sorry. This sorry. It's not this intersection. That's already covered by the refinement. I'm sorry. Such that only finitely many, it's neighborhood V, only finitely many F1 to Fn in F are non-zero on V, and then I take those F's because otherwise it didn't make sense, are non-zero on V, and then you take those F's and they sum up to 1 on V. And the whole business about paracompactness and this local finiteness, which is then mirrored again here, it wouldn't work without that, is to get a sum with a finite upper limit. Because this way you avoid issues of convergence. If you had an infinity here, you would have a series, and then you would have to worry about convergence. And later on, when we use paracompactness, we simply cannot afford to worry about convergence here. Hence, paracompactness with its local finiteness property saves the day. That will be later on the application. I will only be able to give you very good examples later on once we have manifolds and want to establish integration on manifolds. Anyway, so the idea later on, I'll give you an outlook. The idea later on is that if you have a cover, you have charts, and then on one such open set of the cover, which later on we're going to call a chart, you can go to coordinates and you can, for instance, define integration on this chart, because you define integration on the coordinates. But then you have to patch together the integrals on these different open sets, but they overlap. So what do you do in the overlap? You integrate here and you integrate there, but then you have to somehow mesh this together. You cannot add this, because then you would get double the value you actually want to have. You will have to use this partition of unity in order to smooth the results into each other. This will become clear later. I just want to show you why, or give you an idea of why this is so important. Okay, so this is the, and then the big cloud, a very big cloud, closes. That's a partition of unity subordinate to some cover. Example. Look again at the real line equipped with the standard topology. We already know this is paracompact. Well, this is paracompact, then every open cover should admit a partition of unity. So let's draw again the real line. That's the real line. And now I take, it's true for any open cover, so I take this open cover. I take this open set as U1, and I take this open set as U2. U1 and U2 together constitute an open cover, so it goes on, no? Clear. Now, what is a partition of unity in this case? Well, it's a set of continuous functions, such for every function there exists a set U, such that f not equal to U implies already that P lies in U. So well, I'm in dire need for some colored chalk. Bad luck. Okay, so this will look messy. For instance, I could start one function, so now I draw functions over R. So now I also introduce such an axis. I could go up from 0 to 1, like I reach 1 here. And then I go like this, so this is at height 1. And this would be function f2. And you see, for this f2, there is a set u2 such that, so an f2 is 0 here. For this f, there is a u such that if f is non-equal to 0, at those points, you are in U2. Is that clear? That's one such guy. But now I need another such guy. Okay, so this is supposed to be a straight line. Straight line. And that straight line goes here like this, also at height 1. And that we call F2, F1. And you see this F1 has the property, it's non-zero only on U1. Because once we leave U1, or we go to this point here that is no longer part of U1, F1 already assumed the value 0, and then it continues here at level 0. Do you see the two functions, F1 and F2, over the real line I drew? Okay. Now, are these two functions, if I equip here the 0, 1 interval with the induced topology, as I said I would, and I equip this R with the induced topology, are these two functions continuous? You've got to check the answer is yes. They are continuous. So I found two continuous functions such that for every of the functions, I have only two, f1 and f2, there exists a u in the cover such that the functions are only non-vanishing on this particular u. Well, they can overlap. They can also be non-zero on another u, but they cannot be 0 outside the u that I assigned them, or that I found for them. And now the question is it true that for all p in the space, let's say this one, there exists an open neighborhood, say this one, such that only finitely many f's are non-zero on here? Well, I have only two f's. I have only a cover of 2. It's trivial that there are finitely many. The situation could be worse, but here it's trivial. And the question is it true that on each element, on each neighborhood of the space, the sum of the function is always 1? So I could have taken this point and considered this neighborhood V. Okay? Is it true that at every point of V, the sum of these finitely many functions that are non-zero adds to 1? Yes, it does. Because where this function here is 0, this one is 1. If this one decreases linearly with slope -1, this one increases linearly with slope 1, the sum of the two is always 1. That is this. And now you can maybe imagine, we're not there yet. By far, we're not there yet. But imagine you could define integrals on one subset and on the other subset for a function that goes over the whole space. Then you could use these guys to put weights on the integrals that come, the contributions that come from different overlapping subsets. That's the idea why you want this partition of unity. And you want that this works for finitely many functions, such that if you define here an integral, you can take the sum of integrals and you can exchange the sum with the integral because there's no limit, because you have no series to infinity. You don't have to worry about the exchange of limits of sums and integrals. In the definition of an integral, there is a sum. In the definition of the series with infinity up here, that's actually, of course, you know, the limit of the partial sum, so it's also a limit. And if you want to exchange them, when can you exchange, under what circumstances? Very roughly speaking, can you exchange limits and integrals? If the sequences are, pardon me? No, uniformly convergent. Uniformly convergent. Okay, anyway, just as a reminder and as an outlook. So at this point, this is just an example. So these partitions of unity, they come with this formal cloud of stuff. But in fact, the idea is extremely simple. And paracompactness guarantees you have only finitely many such interpolating functions, if you wish, meshing functions. That's the whole point, and that is why we will need it. So the next two topological notions we're going to look at are connectedness and path connectedness. And they're very useful indeed because they tell us whether a space consists of one piece or several pieces. Okay? And if a topological space consists of several pieces, in a certain sense to be defined, then you can study the individual pieces. So you decompose your whole space into building blocks, and you understand the space from the building blocks. So it's a basic principle that you try to understand things from the building blocks. So definition, a topological space M, O, is called connected unless there exist two non-empty, non-intersecting open sets A and B, such that the entire space M decomposes into A and B, and because A and B are non-intersecting, it's a disjoint union, so sometimes one puts a little dot on top of here in order to emphasize that fact. That is connected. So, example, if you take the real line and you take out the empty set, and you equip this with the standard topology, with the topology that's induced by the standard topology on that subset. What else, if I had said nothing else, would be this. You look at this set, and this set is not connected. Not connected. And the intuition is quite simple, because let A be the interval from minus infinity to 0, both exclusively, and let B be the interval from 0 to plus infinity. It's clear they're both non-empty. They're both non-intersecting. And they're both open. In the induced topology, so for short, I will call this induced topology curly O. They're both open. And M is clearly, if this is the set M is clearly the union of the two. That's it. So this is clearly not connected. Now, very useful theorem, a little work to prove, is that the interval 0, 1 equipped with induced topology from R is connected. Once you know that, you can show a number of different things. Now, one of the aspects of looking only at connected parts of your space is that a rather weird property of topological spaces, namely that you can have sets that are both open and closed at the same time, is removed on such connected pieces, on connected topological spaces, or on individual building blocks if the space is not connected. Of course, not for the empty set in the entire set, because that is always open and closed, but we have the theorem. A topological space is connected if and only if the empty set and the entire set, so I should say a topological space MO, is connected, if and only if the empty set and the entire set are the only sets, only subsets, that are both open and closed. Okay, so let's try to prove that. To get some practice in working with this notion. So let's first try to prove this direction. So you see you have an if and only if. So you have an arrow in one direction, arrow in the other direction. Let's first take if connected, then 0 and M are the only subsets that are both open and closed. So let's do this by contradiction. Suppose there is another set U, subset M, that is open and closed at the same time. And obviously another, by this I mean U is not the empty set and U is not the entire set. Suppose you got such a set, open and closed set. Then you can write M equals U union M without U. Well, that's always true for any subset. But now the interesting part here is U is open by assumption. It's also non-empty by assumption. Now, this set, M without U is open, so M without U is closed. But U is also closed. So M without U is open again by the virtue of U being closed. So this is open again. And it's also non-empty. It could only be empty if U was M, but U equals M is also excluded. And by construction, it's a disjoint union. U has no intersection with M without U. So in fact, we found a decomposition into open, non-intersecting, non-empty subsets under the assumption that means M is not connected. But it was the assumption that M is connected. We assumed the negation of the conclusion, and we obtained, that implies the negation of the assumption. That's exactly our proof by contradiction. Hence, this direction is proven. Connected implies only zero, and only the empty set in M are open and closed at the same time. So let's try to go in the opposite direction. So we assume M is not connected. Well, that immediately implies there exist non-empty, non-intersecting, open subsets A and B, such that M can be written as a decomposition of the two. But then B must already be M without A. It's also clear. So we wanted to show that there's another so now A is open, hence M without A is closed. Aha. But because A is non-empty and B is also non-empty, A cannot be the entire set. Hence, that is closed. Hang on, A must be open, but we already knew that. But B is open. So B is open. So M without A is closed, but it's also open, because this is B. Okay? No, you're not? Yeah. It's also open because it's not B. And thus, A must be closed. Thus, we have a set A that is non-empty. That's not the entire set, because otherwise B wouldn't be non-empty, and it is closed. But it was open as well, so it's closed and open. And this is not the empty set or M, as I just argued. So if M is not connected, then it follows you can construct a set that's not empty, this empty set, or the entire set that's both closed and open. Hence, you have the opposite direction. That's it. Okay. So in a sense, this kind of reconciles our intuitive notion of open and closed being incompatible. Well, for the extreme cases, it still is and must be compatible, but for the other cases, it's excluded if you look only at a connected piece of your topological space. Now, intuitively, there is another notion of connectedness, namely if you can walk from one place to the other along a continuous curve. And in fact, that's a stronger notion of connectedness, which is also very important. Definition. a topological space MO is called path connected. It's called path connected if for every pair of points P and Q in the set, there exists a continuous curve gamma with the parameter range 0, 1 into M, such that the curve starts at the point P and the curve ends at the point Q. And the key point here is that the curve be continuous. So examples. RD with the standard topology is path connected. The proof or the sketch of the proof is very simple. Take 2 points PQ out of RD and define the curve by starting at P and going lambda times Q minus P. And lambda is the parameter. So I should write gamma of lambda is P plus lambda Q minus P. And the addition here and the multiplication with scalars is the component-wise defined addition and multiplication with scalars on the D tuples here. And this curve, it can be quickly checked, is continuous. It's just a straight line connecting the two. And in the standard topology, that's continuous. So between any 2 points, there exists such a curve. It's the first example. The second example, for a not path connected space, one has to work a little harder. We define the set S. How does that look? That's a graph x 1 over x. No, hang on, that's sine 1 over x. And the x comes from the interval 0, 1. But the 0 is excluded. And you also have to take the point 0, 0 into it. And all of this is supposed to be considered as a subset of the plane equipped with the standard topology. And then, of course, this subset inherits a topology, and we should look at what this set is. So if I have the plane here, the R2 plane, the tuples, there's the 0, 0 lying, then this thing looks, for x going to 0, looks crazy, okay? Somehow like that. And the space we're talking about is this space S. So the set of these points, the points of the graph. And out here on R2, we have a topology OS, and we equip this subset S with the induced topology on S. And that is the topological space we look at. And this guy is not path connected. Not path connected, but it is connected. So this is an example that connectedness is weaker than path connectedness. And indeed we have the theorem that path connected implies connected. And this example here shows that in general, and that means it doesn't, go the other way around. So let's try to prove this. So assume a space is connected, so by contradiction, suppose the space MO is connected, but is not connected, but path connected. Okay, is path connected? Is path connected without being connected, but not connected? That would be in direct contradiction to this theorem, and we want to derive a contradiction from this. MO is path connected but not connected. Well, if it's not connected, then immediately it means there exist non-empty, non-intersecting open sets AB such that the entire set decomposes. That's not connected. Now, if these two sets are non-empty, we can choose points, a point A in A and a point B in B. If they were empty, that would be a problem. Choose A in A and B in B. Since the space MO, by assumption, is path connected, that means there exists a continuous curve, gamma, from 0, 1 into M, such that gamma of 0 is A and gamma of 1 is B. It's a continuous curve, and that's really very important. Now we can actually look at the pre-image of M. The pre-image of M under gamma, well, that must be the whole domain of gamma, and that's the range over which the parameter runs. That's clear. It's the pre-image of M under gamma. But we know that the pre-image gamma, that M is A union B. But what do we know of the union, of the pre-image of a union? Well, we know the pre-image of the union is the union of the pre-images. If in doubt, write down the definition of the pre-image. This is totally obvious. It's the union of the pre-image of the union is the union of the pre-images. Now A and B were non-empty, non-intersecting, they were open. Now gamma is continuous and A is open. What do we know about the pre-image of an open set under a continuous map? The pre-image of open sets are open. So this here is open, and this here is also open. Now, A and B were non-intersecting. Hence, these are also disjoint. Right? Well, a point and a parameter cannot map you at the same time into A and B if A and B are disjoint. Hence, these two sets are disjoint. And the question is, are they non-empty? Yes, they're non-empty because there's an A and a B and B that are at the endpoints of the curves. So they're open and they're both non-empty. So at least the 0 is in here, and at least the 1 is in here, because A and B, and the curve endpoints being A and B. They're also non-empty, and they're non-intersecting. hang on, what do we want to show? Ah, yeah, sure, no, everything is fine, everything's fine. So that means we have the interval from 0 to 1, and we decomposed it into two open, non-empty, non-intersecting sets. That implies that the interval 0, 1 is not connected. Now we start with the not connectedness of the topological space. We now have the not connectedness of this interval, and we know that is not true. That's a contradiction. Hence, a space cannot be connected, a path connected but not connected. End of proof. Okay, questions here? Now, there is a notion of simple connectedness, and I could define this now, but I rather decide to move this to the next section, which we're going to study now, where it also, this question for simply connectedness and so on, leads to the very important notion of the fundamental group. So we have 2.8 homotopic curves and the fundamental group. So far, we constructed topological properties. Again, that's a property of a topological space that has been constructed solely from its topology. So far, we considered topological properties of a yes-no character. It's Hausdorff or not. It's compact or not. It's connected or not. It's paracompact or not. Yes, no, yes, no, yes, no. Now we're going to define group-valued properties. So the property is not yes or no. The property is the group with two elements and that operation on it. Okay? And again, if two topological spaces are associated with different groups, well, like we're going to define them, then they cannot be homeomorphic. But still, again, unfortunately, it doesn't suffice to check for two topological spaces that they have the same groups, for instance, same fundamental groups, to already conclude they're homeomorphic. I repeat this again and again. There is no such list of properties. Anyway, so first we need an auxiliary notion. That's the notion of two homotopic curves. Very, very intuitive notion. I'll draw many pictures. So two curves, gamma from 0, 1 into a topological space M, and delta from 0, 1 into, well, a set M that underlies a topological space, where MO is a topological space, are called homotopic if, and now we use a lot of what we did so far, if there exists a continuous map, let's call it H, like homotopy. There exists a continuous map H that takes you from 0, 1, Cartesian product 0, 1. Of course, both of those equipped with the induced topology from the standard topology, and then the Cartesian product being equipped with the product topology. So this is all a topological space into the topological space M, and only because we know the topology here on this whole set, and we know the topology here, we can meaningfully talk about a continuous map. If there exists a continuous map H0101 to M such that, well, you can think of this parameter as still being the parameter that was here for the individual curves, and the other parameter as one that interpolates between the curves, so more precisely such that H of 0, lambda simply reproduces the curve gamma for lambda in 0, 1. And h of 1 comma lambda reproduces the curve delta of lambda. Okay? And obviously for all the intermediate values, that must be curves. Well, where do they lie? Well, because of the continuity, intuitively, they lie in between. So pictorially, okay, sorry, I should have taken two curves, no problem here, with the same starting and end point. I think that is what I want. Yeah, that's what I want. So where gamma of 0 is delta of 0 and gamma of 1 is delta of 1. So let's take two curves that start at the same points. Let's say this is gamma, and let's say this is delta, the curve. And then the homotopy, in a sense, you have lots of curves intuitively that lie in between, and you can continuously deform the curve delta into the curve gamma, and this guy here in between would be, for instance, h1/2, comma, open slot, because it's the entire curve that lies in between there. And the whole statement of delta or gamma can be continuously deformed into delta is formally encoded in the idea that you have one continuous map on this product space. So whenever somebody talks about continuous deformation, it's something like this. Okay, interpolating map here. Okay. Now, we can define an equivalence relation. We can call two curves with the same start and end point are called equivalent. Well, we already did that. We already called them homotopic. Okay. Being unnecessarily repetitive here. So let's say two curves with the same starting and end point, gamma and delta. We use the symbol if gamma homotopic, if gamma delta are homotopic. And it's a fact that this is an equivalence relation. Well, every curve is homotopic to itself. That's easy to do. If gamma is homotopic to delta, then delta is homotopic to lambda. You get this by just, well, having something at h of 1 minus sigma, and then you let sigma run. And it's transitive, well, you can check, but it's intuitively clear. If you can continuously deform delta into gamma, you can deform gamma into epsilon, then you can also continuously deform delta into epsilon. It's an equivalence relation, and we know the nice thing about equivalence relations is that they come in handy in putting on your glasses your equivalence, your quotient space classes, and only see the classes, no longer the individual representatives. And in order to do so, we first define another class of curves where we'll apply this, and that's the space of loops definition. Let MO be a topological space. Then for every P in M, we define the space of loops at the point P as, call this guy curly L, the loops at the point P, and those are all the continuous curves, gamma, from 0 to 1 into M that are continuous, nice, but where also the starting point coincides with the end point. So quite obviously, this is a loop. Okay, that's the space of loops. Now, on this space of loops, we can actually establish a, well, concatenation, define. How do we call this? Star. Star, what does star do? Star takes a loop at the point P. Well, strictly speaking, it's star at P. Okay. It takes a loop at P, and it takes yet another loop at P, and it constructs from it a new loop at P. How does it do that? Well, it takes one loop gamma, star, a loop delta. So gamma, delta are now loops, same starting end point. If they're a loop, they have a range from 0, 1. So for some lambda that runs from 0 to 1, inclusively, both sides, we define this concatenation as gamma of 2 lambda for lambda for 0 less or equal to lambda less than 1/2, or less than 1/2, and delta of 2 lambda minus 1 for 1/2 less or equals to lambda less or equal to 1. And this guy here we call the concatenation operation, and it produces a new loop. And the intuition is you have one loop and you have a second loop, say this one. What you do, if you concatenate them, you get one loop. That's the following loop that consists of, you run through the first loop at double speed. Well, speed doesn't matter to the topology. And then you run through the second loop, because at 1/2 you are at 0 here, and you run to 1. You then run through the second loop, and you come back, and the whole thing altogether is a loop, because it's the same starting and end point. And yeah, so these are those guys. You have this concatenation of loops. Now, it's very silly to look at this thing where, well, what's the difference between this picture and this picture? I mean, apart from them being at different points, I want them at the same point. Well, it's slightly different because my copying capabilities are not so good. But you say, well, that's the same thing. It's the same situation. Well, it becomes even more the same situation, or more obvious, if here you had taken out, if so before the blackboard was the topological space M, but now take this point out, remove this point. Then this loop encloses this point, and this one doesn't. And we know that these two loops cannot be homotopic, because I can no longer continuously deform one in order to produce the other. Intuitively, it's clear, because this hole, I mean in the plane, this hole prevents me from going over it in a continuous way. It's the intuition. So these are not homotopic. And what we would like to look at is not the space of loops, but at the space of loops modulo homotopy. We don't care where exactly the loop lies, as long as the situations are continuously connected. So, definition. The fundamental group, and it has a name, it's called pi, and because the other groups that can be built in higher, well, if you don't come from a circle, well, we come to that in a second, we call it pi 1, the fundamental group pi 1 of a topological space is the set. Okay, the group must be a set together with an operation, and the operation is called blob. Of a topological space is the set. Well, what's the set? It's the set pi 1, and pi 1 is the Well, it's the fundamental group at a point, to be precise, at a point. Is the set pi1 at a point, is the loops at that point, quotient space, the homotopy. Intuitively, it's very clear. Ignore everything that can be continuously deformed. Okay? It's the loops, but under identification of all the loops that are homotopic to each other, together with the blob operation, and blob takes you from pi1p cross pi1p to pi1p, as it should. And so pi1 consists of equivalence classes of loops, because this is a quotient space. The quotient space is, of course, I remind you, is the set of all equivalent classes of loops. So gamma in LP, and this is the equivalence class with respect to the homotopy twiddle. But that's just a reminder. This says it all. And so because the fundamental group space is a quotient space, if we establish the blob operation, we might want to do this by representing the individual loops at the point P by actual loops. And we define this as the equivalence class that you get by concatenating the loops. It was the star operation from before, where we first went through one and then we concatenated with the next, and we take the equivalence class after that. So it's a definition by using representatives. So obviously what you need to do, you need to check whether it's well defined. Well, I assure you it is well defined, but you're invited to check at home. And so what you do have here is you have this guy, this set with this blob operation, and this blob operation is associative. What is the neutral element of the blob operation? What's the neutral element? Which delta do you have to put here in order to get this class here back? Well, it's the constant curve that always stays where you started. No? So the identity curve, the gamma it, is the curve from 0 to 1, 0, 1 to m, where gamma of lambda, so at the point P, there's always base point P, that stays at the base point P. You can concatenate that with the other, you get the same curve, at least under homotopy. And what's the inverse element of this operation? Well, you have a curve, and you want to get back, if you do this blob operation, you want to get the equivalence class of the identity curve. So how do you do that? Well, you choose the second curve and you run through it backwards. Is that true? Yes, that's true. You run through it backwards. So, okay, so you also have an inverse. So that means we know nothing about commutativity, but we have a group structure. So this guy is a group, it's called the fundamental group. Now, an example, or several examples, are in order. Well, the first example is, let's forget about the boring examples, okay? So let's start with the interesting examples. Let's take the sphere, the surface of the sphere. So what I mean by this, I mean the topological space that you get by considering, say, the unit sphere in Rn and pulling back or inducing the topology from the R3 that's around it, and then you get a topological space. You then forget about all the unit business and so on. You only think about the topology, it's the surface of the sphere. Now I go to a point P, and I make a loop. Okay. How does this loop differ from any other loop I have? By differing, I mean up to homotopy. The answer is all the loops are homotopic to each other. Okay? So that means the equivalence classes, the set pi1 consists of just one element, and in particular they're all homotopic to the identity. So to the curve that stays always at the point P. There's only one class in there. The group consists of one element. So one element group. And that is its own inverse. You need, a group always needs at least one element because there is the existence of a neutral element. Okay, so that's very simple. That's a very simple fundamental group. Now let's do something slightly more interesting. Let's take the so-called two torus. I haven't told you what the torus is. Well, now I do. The torus is the Cartesian product of two circles. We already had the circle as a topological space. Now take the Cartesian product of the sets, equip the sets with the product topology, and you got the topological torus. Well, I should write here top. I can draw a picture of the torus. It's the surface of this donut. Okay. By the way, up here it wouldn't have made the slightest difference if I had drawn the sphere like this, because shape is something that is an intuition of ours, but topology doesn't provide a shape because it's two spaces of different shapes like these two are actually homeomorphic. So through the glasses of topology, they are the same. It's just the artifact of my presentation of these spaces on the blackboard that makes them look different. And they're homeomorphic, if you wish. And well, obviously, if they're homeomorphic, they must share all their topological properties. This is compact, this is compact, this is connected, this is connected, this is path connected, this is path connected. It has fundamental group just consisting of the identity and so on. So now here we have the torus, and now I start at a point P. Now, how many different, well, maybe we should have first started with example C. We come back to B, and we take the cylinder. And the cylinder is just the product of the real line with the circle. Now, the circle we already had as a topological space. The real line, we equip it with the product topology. And this is, well, actually, you know how this cylinder looks like. And of course, it never ends. It's the cylinder. It goes like this. Now, if I have a point P here, I can look at a loop that just looks like this, right? So the identity is again in there because you can contract this to the identity that's homotopic. Now, however, I can also go up here, and then on the back, I can wind around the cylinder. Now, this one, because the cylinder is infinitely long, intuitively speaking, I can never deform the loop that goes around the cylinder into the identity. I can't. But now I can do another thing. Well, I take another point, but you see that it's, in principle, it's the same point, right? It's just for my picture. You can go around once, and then you go around a second time, and only then you return. So you wind around the cylinder twice. Can you deform this into the curve that winds around the cylinder only once? Also not. So for the cylinder, you get actually pi isomorphic to, and then you can go in this direction and you can go in the other direction. Now an interesting question is whether that's homotopic. If you go a curve in this direction, you go in the other direction, are they homotopic? I don't think so. Think about it, because you have to check with this continuity map. No, I don't think so. So the fundamental group, if I'm right, here is then the set is the integers, because you can wind around to the right, you can wind around to the left, and neither of those can be transformed in any of the others. And the 0 is the one that's the identity. And obviously, if you concatenate them, then you add. So as groups, the fundamental group with the blob as a group is isomorphic to the integers with the addition. And what does isomorphism as a group mean? Well, it's of course bijective, right? But then it also respects the group property. So there must be a map between these two that is bijective and respects the group property. So that means there exists a map F from pi 1 to z that's bijective, and respecting the group property would mean you can first take two elements alpha and beta and blob them, and that should, however, be the same as taking alpha and taking beta and adding them on the other side. That would be the structure preserving map if you have a group structure. Okay. Yeah?
Can't we actually presume that we maybe take a cylinder that hasn't got a constant radius? If we like vary the radius?
Yeah, but that wouldn't.
Because then we could wrap around the bigger radius of the cylinder and then the smaller radius.
Yeah, but that topologically, that wouldn't make a difference because you wrap around here, okay? But now you can also take another curve that goes here, then wraps around here, no? But those can be deformed into each other. Think of strings. To really take a string, go around, and wrap it around something. But it's, well, a string, it's a rubber band. And then you can deform it continuously without breaking it. Okay? Well, that's the intuition, but you should always refer to the existence of a homotopy H that interpolates between the curves. But topologically, this is not seen, the difference. Okay. So now let's go back to our example of the torus. Well, now, intuitively speaking, I can wrap once, twice, 3 times around the inner hole, if you wish. But I can also wrap around this part that's like a piece of a cylinder. But anyway, I also don't get out. It's not infinitely long, but it's cyclically identified, right? I also don't get out. So I have a winding number in this direction, and quite independently of that, I have a winding number in the other direction, around, well, here once around here, and then it runs around here. So here, the fundamental group will consist of this, will be the Cartesian product of these. And, well, as groups, so if you then take the fundamental, okay, hang on. So I should write, sorry, this was the fundamental group is this, right? And if you take the product here, the blob here, I think the blob here corresponds to the pairwise addition here, because you can go around n times in this direction, then you add or you concatenate with that direction, and you go around this, but it then doesn't matter with which order and so on. So I think the fundamental group of the torus is this, okay. And so immediately you see this group is a different group from that group. So the two-sphere has a different fundamental group than the torus does. So they can never be homeomorphic because the groups are constructed from the topology alone. From the topology alone. Okay? They cannot be homeomorphic. Neither can the cylinder be homeomorphic to the torus or the cylinder to the sphere and so on. But again, no collection of topological invariants. One can also call them topological invariants because they're invariant under homeomorphism. No collection of topological invariants. Let's call them Hausdorff, yes, no, compact, yes, no, connected, yes, no, fundamental group, well, not yes, no, but group valued. No such list exists such that for two topological spaces MO and NO twiddle, you could check if they're all the same. Say this is the group G, and this one has it, or doesn't have it, and it also has the group G and so on. So no such list here is known, such that if you check for two spaces that all the properties, the spaces agree on all the properties, no such list is known that would then allow to conclude such that one could conclude that MO is topologically isomorphic, so it's homeomorphic to NO twiddle. It'd be great if we had such a classification. You just had to check all the properties, but no such list is known. That is something I was referring throughout this section. And this also concludes our, well, quick overview and selection of topological properties that will be important for us later on. And virtually all of these properties I pointed out will make their appearance later on in the course. And of course, there are many other topological properties, but now you don't need to be afraid of any topological property. You look up the definition. It's always defined in terms of the open sets. And you know no such property can distinguish reliably non-homeomorphic spaces. See you next time.